All right. Everyone, welcome once again to the set theory seminar. And we have one of our old good CUNY people back, Brent Cody, who is at Virginia Commonwealth University. Brent, it's great to have you back again at CUNY in some form or another. And he will be speaking today on sparse analytic systems. Go ahead, Brent.
Okay, thank you. So yeah, I'm going to talk about sparse analytic systems, and this is some joint work that I did with Sean Cox and one of our undergrads at VCU, Kayla Lee. We worked on this this past summer. And I think it's a nice topic, and there's several very approachable open questions, so hopefully find it interesting. Okay, let's see. Can you guys see my pointer?
Yes.
Okay, good. Okay, so let's start with this question. So if you're given a function with domain some initial segment of the real numbers and codomain the reals, can you predict what the function's value at t should be, where t is the right-hand endpoint of this open interval on which the function's defined? So just think about that for a second. So there's no requirement that this function f needs to be continuous or anything like that. It's just an arbitrary function. So of course the answer is no, right? There are many possibilities for such a guess, but in a sense you can make predictions like this. So let me explain. So you get out your crystal ball to make this prediction, and you take a well ordering of the set of functions from the reals to the reals. And you take capital F to be the least element of the set of functions, the set of total functions that agree with this function that you start with, the function you want to predict. Okay, and you use that capital F to make your prediction. So you predict that the value of little f of t should be the value of this capital F of t, where this capital F is just coming from this well ordering given by the axiom of choice. Okay, so it seems like kind of a silly way to make predictions like this, but it turns out that these are actually pretty good. So Hardin and Taylor showed that if you take any total function h from the reals to the reals, then the set of real numbers t, such that the prediction made using this method on the initial segment of this total function, that set of t where these predictions are wrong is measure 0. So in fact, it's countable and nowhere dense. And this just comes from the fact that this set of bad prediction points that we're looking at here, the set of these t values where the prediction doesn't work, is well ordered. You can argue that if you had a decreasing chain of bad prediction points, that would lead to a decreasing chain in the well ordering that you started with, which of course can't happen. Okay, so this leads to the definition of predictors. So if you take S to be any set, and then we use this notation to note where we put a little smiley face under the real numbers. This notation denotes this set of functions from initial segments of the reals to the set S. Okay, then an S predictor is any function P from this set of functions on initial segments of the reals to the reals. Okay, that's an S predictor. And an S predictor is good if for all total functions, capital H defined on all the reals into S, the set of t values at which your prediction is incorrect is measure 0. Okay, so an S predictor is just a function that makes the predictions, and we say that an S predictor is good if it makes a lot of correct predictions, right? If for every total function, it makes a correct prediction on a set of full measure. Okay, and then the theorem that Hardin and Taylor proved is that every set S has a good S predictor. Okay, so here, this is slightly different from what we did in the first slide, because here we were looking at functions into the reals, but essentially the same definitions and proofs for any set S.
Do you get in the general setting also that the set of points where it's wrong is countable, or?
Yeah.
Because you talk about measure 0 here, but
Yeah.
Okay,
So
all
the
right, okay.
definition of good is measure 0, but in fact, in this theorem, if you look at the proof, yeah, the set of where you get bad prediction points, that set is countable and nowhere dense.
Okay.
Yeah. Okay, so Hardin and Taylor also wondered how robust these good predictors can be. So in other words, if you start with some function f, little f, that you might want to predict, so some little f whose domain is an initial segment of the reals into S. Okay, and if you take that little f and you just shift it to the left and write down this function g. Okay, so g is a shift of this function f. G of x is equal to f of x plus b. Is there a good S predictor such that P gives the same prediction for f of t as it does for g of t minus b? So in other words, if you take a function and this predictor is making a prediction for the next value of this function, if you shift that function over, can you have a predictor that makes the same prediction for the shifted function, right? So how robust can these good predictors be? Okay, so that leads to this definition of anonymity. So for a class of homeomorphisms, gamma, and this little plus on the homeomorphism notation, that just means strictly increasing. Okay, so we're looking at a class gamma of strictly increasing homeomorphisms of the reals. We say that an S predictor is gamma anonymous if for every function in this class, phi, and for every function f that we might want to predict, the prediction made by this predictor of f is equal to the prediction made by f precomposed with phi. Okay, so this idea comes from what Hardin and Taylor did involving shifts of functions. Okay, so a predictor is gamma anonymous if you can if you start with a function and you shift it around using some function from gamma, or maybe you can think of these functions phi as maybe scaling the domain or shifting the domain somehow. Then the predictor is anonymous for those functions if it makes the same prediction, no matter how you manipulate the original function you might want to predict by precomposing. Okay, so Bajpai and Velleman showed that every set S has a good predictor that's anonymous for affine strictly increasing homeomorphisms. So there, by affine, we just mean linear. So that's a positive result, telling you that good predictors are somewhat robust. You can sort of scale and shift the domain however you want using a strictly increasing homeomorphism, and you can have a good predictor that's anonymous for those types of functions. Now, the proof of this theorem is different from Hardin and Taylor's. It's a little more involved. You have to do more work. It's not that any good predictor will work to have this type of anonymity, but and they also, Bajpai and Velleman also proved the negative result, which says that if you ask for anonymity for a large enough class of strictly increasing homeomorphisms, eventually you won't get that anonymity for every set S. So there is an equivalence relation on the reals, tilde, such that if you let S be the equivalence classes of that equivalence relation, then there's no good S predictor that's anonymous with respect to the C infinity strictly increasing homeomorphisms. So C infinity, of course, just means infinitely differentiable. Okay, so we get a positive result from Bajpai-Velleman for affine strictly increasing homeomorphisms. So we can have good predictors for every set that are anonymous for the affine functions. But asking for good predictors anonymous with respect to C infinity functions is somehow too much. You're asking too much. You can find sets that do not have good predictors that are anonymous for C infinity functions. Okay, now, and then there's a natural question, which is, okay, because there's a pretty good big gap between affine functions and C infinity functions. So there's a natural question about, other classes of functions that live in between the affine and the C infinity functions, right? So here's some other classes of functions. So if you have the strictly increasing homeomorphisms at the top, and all these subsets or most of these are subgroups of this group of strictly increasing homeomorphisms. So,
Brent,
yes.
Could I just ask you a quick question? So
Sure.
yeah, so there it all depends on the class of functions, but also on this S. And I'm kind of wondering if you could give some intuition about the role of S. Like at first sight, it seems like if you make S bigger, it will be harder to guess because there are, so to speak, more options. But on the other hand, it seems to be making it harder when you factor it by some equivalence relation. So I'm kind of, is there some intuition about the role of S there? About the target set?
Actually, that's a good question, and I don't really know how to answer that. So like, what the question here is going to be whether or not every set S has a good predictor that's anonymous with respect to some class of functions. And
Right.
asking about different S's, that's an interesting question, and I don't know how to answer it.
Okay.
Yeah.
All right. Thanks.
Yeah. Yes. So the question we want to ask is, does every set S have a gamma anonymous good predictor for various gammas? Okay, so consider the gammas here in this diagram. Okay, so what was known previously was for these somewhat small classes, so the Bashby-Velleman result that we just discussed says that yes, if you take gamma to be the affine strictly increasing homeomorphisms, every set S has an affine anonymous good predictor. But if you ask for C infinity anonymous good predictors, that's too much. You don't get those for every set S. And then recently, Sean Cox and Matthew Albers sort of improved the Bashby-Velleman result to a slightly smaller class of functions, which are the infinity Lipschitz diffeomorphisms. So there they proved the negative result. So if you ask for a good predictor for every set that's anonymous with respect to D infinity, that's still asking too much. Okay, you don't have those. And Bashby-Velleman asked specifically about the class of analytic strictly increasing homeomorphisms. Does every set have a good predictor anonymous for the analytic strictly increasing homeomorphisms? And so we answer this question under CH. So if you assume CH, the continuum hypothesis, then the answer is no, that not every set has a good predictor anonymous with respect to the analytic strictly increasing homeomorphisms. It's open whether or not CH is necessary here. Okay. So if CH is false, maybe you can have good predictors for every set that are anonymous with respect to analytic functions. And then also in this diagram that for polynomials, this is also open whether every set has a good predictor anonymous for the class of polynomials that are strictly increasing. Okay. And that seems like a very approachable problem, and there I think the answer is probably yes, but I don't know. Okay, we'll come out. I'll phrase those open questions at the end too. But... Okay, so the theorem says that if you assume CH, it's not the case that every set S has a good S predictor anonymous for the analytic strictly increasing homeomorphisms. Okay, so let me sketch how we prove this, and then we'll dig into some parts of the proof. Okay, so we can show that CH, if you assume CH, then you can build what we call a sparse analytic system. Okay, we'll talk about what that is. Okay, and then you can use the sparse analytic system to build an equivalence relation on the reals, sort of mirroring what Bashby and Velleman did. for their negative results. You can build an equivalence relation on the reals such that the set S consisting of the equivalence classes of that equivalence relation, that set has no good S predictor anonymous for the analytic strictly increasing homeomorphisms. So this is an outline of the proof. And so what we're going to do first is talk about sparse analytic systems and what they are. And then we'll talk about why CH implies that these things exist. And then I'll say a little bit more about the rest of the proof.
Brent, sorry
Yes.
to keep interrupting. Just another question. So you're always interested in homeomorphisms that are strictly increasing and all these variations of these questions? Okay. So
Yeah.
so with the polynomials, I mean, there are only linear polynomials that are strictly increasing, right? So
Oh, let's see. I guess yeah, maybe not strictly increasing. That's not what I want to say. I want to say just increasing.
I see.
The derivative could be 0 in some places. Yeah, sorry.
X cubed plus X is strictly increasing.
Oh, X cubed plus X.
Oh, yes. Oh, I'm so sorry. Yeah,
Okay.
I was just completely sorry. Okay, right.
Well, then the
No,
question of what I actually mean. Let's see.
And maybe,
Yeah.
I don't think you mentioned, but just to point out that there are only two kinds of homeomorphisms from the reals to the reals, strictly increasing and strictly decreasing. And strictly decreasing wouldn't make sense in the context where you're predicting a value on the basis of earlier value.
Right.
I see. Yeah, that makes sense. So I do mean strictly increasing. And
Right.
let's see.
Yeah, and I was just completely forget about my question. Sorry.
Thank you. And that was Andreas. Thanks, Andreas, for the help there.
Okay.
See. Okay. So yes, so this is the plan. So let's talk about sparse analytic systems first. Okay, so to define sparse analytic systems, let's go back to an old problem, Wetzel's problem for the 60s, which is the following. So if you have F, a family of analytic functions defined on some common open domain D of the reals or the complex numbers, such that for every point in the domain X, the set of images of that point under all members of the family is countable, must it follow that the family itself is countable? Okay, that's Wetzel's problem. Notice that if you remove the requirement that the family be analytic functions, that the functions in the family be analytic, you deleted that word, then the solution is trivial, right? Like, because if you look at all functions from the natural numbers to the natural numbers, right, that's an uncountable family, but if you fix any point, the set of images of that point will be countable, right? Okay, so this requirement of analyticity here is important. So Erdős showed that Wetzel's problem is undecidable. So he showed that 1 and 2 are equivalent. So the first item says there exists an uncountable family of functions, as in Wetzel's problem, so defined on some fixed open domain of the reals or the complexes, such that for every point, a set of images is countable under the family. And that's equivalent to the continuum hypothesis. Okay, so this is a really nice proof. If you haven't read it, I encourage you to take a look at it. Erdős, his paper is only 2 pages long. It's a really nice proof. It's easy to work through, but you know, surprising and some profound insights in this 2-page paper. This is one of the proofs that appears in the famous proofs from the book. Okay, but these types of families of functions motivate the definition of sparse analytic system. Okay, so these uncountable families of functions, which have the property that if you fix any point in the domain of these functions, the set of images of that point is countable. Okay, so here's the definition of a sparse analytic system. So a sparse analytic system is a family of functions indexed by points in the plane. Okay, so F sub P, where P is in R2, such that for each point P in the plane, F sub P is an increasing analytic bijection from the reals to the reals. And that passes through the point P. And item 2, this is the sparseness condition. It says that for each point Z in the reals, the set of images under functions from this family whose indices do not have x coordinates equal to Z must be countable. Okay, and also for this fixed Z, the set of pre-images under all functions from this family whose y coordinate is not Z, that must be a countable set. Okay, so this is these types of families, sparse analytic systems, are similar in a sense to the families of functions that come from this theorem of Erdős. Notice that, in Erdős's theorem, you have sort of a sparseness condition. This countability is like a sparseness condition on the set of images, but in sparse analytic systems, we require two types of sparseness, right? A sparseness for the set of images and also a sparseness for the set of pre-images. So here's a picture down here. So, these members of these families, these sparse analytic systems, are strictly increasing analytic bijections indexed by points in the plane, such that f sub p has to pass through the point P. And if you take any Z, which is not equal to x sub p, and you take the set of images of that Z under all members of the family, you have to get a countable set. And then if you look at Z on the y-axis, and if Z is not equal to the y coordinate of P, then when you take the set of pre-images of that Z, you have to get a countable set. Okay, and if that's the case, then you have a sparse analytic system. Okay. Okay, so the theorem, one theorem here is that the following are equivalent: the existence of a sparse analytic system and CH. So you can think of this theorem as sort of being a strengthening of Erdős's theorem we mentioned. Okay, so the proof that A implies B is not so hard. Of course, sparse analytic systems are uncountable because they're indexed by points in the plane. Right? And so to prove that the existence of a sparse analytic system implies CH is fairly easy. You can just take a sparse analytic system and use it to define a family of functions as in Erdős's theorem. And then that implies CH by Erdős's theorem. It's the other direction that's harder, to prove the existence of a sparse analytic system using CH. Okay, so if you assume, so to prove B implies A, assume CH, you can use that to obtain an enumeration of the reals in order type omega 1, as well as an enumeration of R2 in order type omega 1. You can use these enumerations to build a sparse analytic system. We'll talk more about how to do that in a second. Okay, and so what we're going to do is essentially look at one step in this process. Okay, so you use an enumeration of the reals as well as the plane to build a sparse analytic system, a step by step, right? So for each alpha less than omega 1, we have one step. So at stage alpha, to get the alphth member of the sparse analytic system, we apply the next theorem that I'm about to show you. You apply it to the given point that appears at that stage in the enumeration of R2, as well as the countable set W, consisting of the points in the enumeration of the reals that appear before stage alpha. Okay, so what is this theorem? This theorem is sort of one step toward building a sparse analytic system using CH. Okay, so that's theorem 3. This is the theorem in the proof that I worked with our undergraduate student on in the summer. So I'm going to go through some of the details. It shouldn't be too bad. Okay, so this theorem, what does it say? So suppose D is a partition of the reals into dense subsets. And for each Z, for each real Z, let D sub Z be the unique member of the partition containing that point Z. It's just a notational thing. Okay, so now for any point P in R2 and any countable set W, okay, think of those as, the the alpha point in the enumeration of R2, and then the countable initial segment of the enumeration of the reals. Okay, so for any point P in R2 and any countable W contained in R, there is an entire function F from the complex numbers to the complex numbers satisfying these conditions. So F restricted to the reals is a real valued function. And it's an analytic function from the reals to the reals. F is also, when you restrict to the reals, is also a bijection with a strictly positive derivative. F passes through the point P. And then item 4 is saying that, in a sense, what we can control the values of this function F on the countable set W. So for each little w in the countable set capital W, as long as W is not equal to XP, we demand that F of W live inside of this dense set D sub W. So in other words, right, by definition, D sub W is the member of the partition that contains W as an element. And what this condition is saying is that as long as W is not equal to XP, F of W has to live in the same member of the partition that W does. And condition B is saying, as long as W is not equal to YP, the preimage of W has to live in the same dense set that W does. Okay, so let's go through it one more time. I know there's a lot here to digest, but so you take, suppose D is a partition of the reals into dense sets. For each real Z, let D sub Z denote the unique member of the partition containing that Z. And then this is saying for any point in R2 P and any countable set W in the reals, there exists an entire function from C to C such that when you restrict that function to the reals, you get a strictly increasing real valued analytic bijection passing through the point P, the arbitrary point that we're starting with, and such that we can control the values of F. We can control the images computed using F on the set W, and we can also control the pre-images of W under F, in the sense that we can obtain such a function so that the images and pre-images live in the correct dense sets. Okay, so this is the theorem. We're going to look at some of the details involved in the proof of this theorem. And again, this theorem is like one step toward building a sparse analytic system. This definition is here. Okay. All right, so before we get into the proof, are there any questions about the statement or anything?
So you say hence analytic. Is that from the fact that it's an entire function?
Yeah. So by entire, I just mean an analytic function defined in all complex numbers.
Okay, right.
And so then if item 1 is saying when you restrict it to the reals, you get a real value function, and then that function is therefore analytic as a function from R to R.
Great, thank you.
Yep. Okay, all right, so let's dive into some details about the proof of this theorem 3. Okay, so we have a fixed partition of the reals D into dense sets. We have an arbitrary point P and a countable set W. Okay, so we can enumerate W as W0 through, W1, etc., WI. We're going to fix some notation here, the star. Let D sub n be the unique member of the partition that contains W sub n. Okay. And now the idea behind this proof is following. We're going to define a sequence of functions f sub n such that each f sub n satisfies conditions 1 through 3. So each f sub n will be a function from C to C such that when you restrict it to the reals, it's real valued, it's a bijection, strictly positive derivative, and it passes through the point. Okay. And each function in this sequence f sub n will satisfy property 4, but not the full version of property 4, but it satisfies property 4 for finitely many of wi's. Okay, And then what we do is take the limit of that sequence of functions and hope to obtain a function that satisfies all these properties. So property 4 for all wi's. Okay, so that's the plan. Okay, so the first step, I should say this proof is inspired by an existing proof from the literature. You can check out this article to see the original proof. There's some details come up here in our proof that weren't in the original article here by Ninehuis and Thiemann, but essentially they, well, yeah, their article is called "On the Existence of Entire Functions Mapping Countable Dense Sets Onto Each Other." So you know that two countable dense subsets of the reals are isomorphic, right? But then there's sort of a natural question about, you know, whether or not you can find isomorphisms, which are actually restrictions of entire functions from C to C. And this was the question that they were working on. Okay, so to get started here, what's the first step in building this sequence of functions that satisfies all these properties 1 through 3, as well as 4 for finitely many wi's? So the first step is to write f0, function from C to C, and just write an explicit definition for it. It's this linear function that obviously passes through the point xp, yp. Okay, so that's pretty good. That's a good first step. And if you look at the statement of the theorem, this function satisfies 1, 2, and 3. It doesn't satisfy 4 at all, necessarily. Okay, so what's the idea? So now, this function, f0, that passes through the point xp, yp, we want, when we look at w0, the first member, or the 0th member of our countable set, and we use this function f0 to compute the image of w0 that lives on the y-axis over here. We want this image of w0 to live in the same dense set that w0 lives in. So we want this image to live in d0. Okay, but of course it might not. So the question is, what do you do if it doesn't live in there? If it doesn't live in the right dense set? So then the answer is you take the f0 function that we wrote down here, and you just wiggle it a little bit so that you get a new function so that the image of w0 does live in the correct dense set. Okay, so what do we mean? How do we wiggle this function f0? So define g1 to be another linear function, which is equal to 0 at xp. And we have a scaling factor alpha 1 there that we're going to choose small enough. So alpha 1 will be a positive constant that's small enough. And I'm not going to say too much about how to choose these alphas until the end. But so then using that function g1, you look at this family of functions, f0 plus m g1, where m can be any real number in the closed interval from 0 to 1. So this family of functions is illustrated on the picture with the green lines. Okay, so you're taking the original function, which is the black line, you're adding all these multiples of g1. But notice, I mean, because g1 is equal to 0 at xp, right, all these functions have the same value at xp. Every function in the family has the same value at xp, namely yp. Okay, so you look at this family of functions and you evaluate all these functions in this family at the point w0, and that gives you that purple line segment. Okay, so that gives you an interval. So when you take this family of functions and you evaluate it at the point w0, you get an interval. And then because d0 is a dense set, it must intersect that interval. So that means you can choose an m1 in the closed interval from 0 to 1, such that f0 plus m1 g1 of w0 is inside of d0. Okay, and now we define f1 to be f0 plus m1 g1. So we use this family of functions to wiggle our original f0, right, a little bit, such that we create this interval, and then we use the density of d0 to choose one point in that interval that intersects d0, and then whichever function from the family that goes through that point of intersection, that's the function that we choose to be f1. Okay. So now we have F1. And now F1 satisfies property 1 through 3. It's a strictly increasing analytic bijection, right? It's a linear function. It passes through the point XPYP. And now by construction, the image of W0 under F1 lives in the correct dense set. It lives in D0. Okay, but we also need this condition on pre-images. So if we look at W0 on the y-axis and we compute its pre-image using this function F1, right? We want that pre-image to live in D0. It needs to live in the same dense set that W0 lived in. Okay, so what do we do if it doesn't? Well, the answer is essentially the same. We take F1 and we wiggle it a little bit, and we choose a new function so that the pre-image of W0 does live in the correct dense set. Okay, so to do that, we define G2. Okay, now G2 has to be 0 at 2 points. We want G2 to be 0 at XP and at W0. Okay, and we have this scalar multiple alpha 2 out in front. And again, that's the positive constant that we're going to choose small enough, right? We don't want to wiggle things too much because we don't want to end up building a function that's not strictly increasing. You want these G functions to always be odd degree so that their derivatives are always bounded below. Okay, so that's the reason for putting this square here, which might seem a little strange, but okay, so we use this G2 function. Okay, this is a cubic function, and it's 0 at XP and at W0. We use this G2 to wiggle the function F1. So we look at this family of functions obtained with the form F1 plus, mg2, where m is in the closed interval from 0 to 1. If we look at that family, it's like this, right? And then we take all the pre-images of W0 using members of this family. That set of pre-images is an interval. So it intersects the dense set D0. And so we can use that intersection point to choose a curve from the family, okay, that is going to work. So F2. So we pick this function F2 to be F1 plus M2 G2, where M2 is such that F1 plus M2 G2 preimage of W0 is in D0. Okay, so now we have 3 points that we've handled, right? And so now, so now going forward, we want these 3 points to be frozen. We're going to keep wiggling things and keep choosing new points so that we control images and pre-images on this countable set, right? That's the idea. Okay, but you do run into a little bit of a roadblock here. Okay, so we've got F2 defined so far in the picture. F2 passes through XPYP. The image of W0 under F2 lives in the right dense set. The pre-images of W0 also lives in the right dense set. Okay, and now we want to build F3, which will equal F2 on this set of 3 elements. Okay, but we want F3 to have the new property that F3 of W1 has to live inside of D1. Okay, so now there's a question about where does W1 live in the domain, right? Okay. So we can assume W1 is not XP, because if W1 is equal to XP, then there's actually no requirement. Right? Remember, go back to statement here. We only need to control the values of F on this countable set W for those W's that are not equal to XP. Okay, so when we're trying to define F3 here, we can assume that W1 is not XP, again, because if it is XP, there's no requirement, so we can just define F3 to be equal to F2. We also know that W1 is not equal to W0 because the WIs enumerate the countable set W. Okay, but what if W1 is equal to the pre-image of W0 under F2? Okay, that seems to be a little more problematic, because if that's the case, if W1 were equal to this pre-image of W0 under F2, well, that's bad, because now we want to control the behavior of the image of W1 but we also need to control the behavior of the pre-image of W0. So there might be a conflict there. Okay, but it turns out there's no conflict. So how do you see that there's no conflict? Well, if W1 is equal to F2 inverse of W0, well, we know that by construction, F2 inverse of W0 lives inside of the right tensor set D0. Okay, but then in fact, that tells us that W1 is in D0. But by definition, remember the star, D1 is the unique member of the partition that contains W1 as an element. So that means that D0 has to equal D1. Right. Okay, and then from that, you can see that F2 of W1 equals W0, of course. And now W0, of course, lives in D0 by construction, by definition. But D0 equals D1, so the image of W1 lives in the correct tensor set. Okay, so there's a question, like when you build this up to a certain point and you're trying to handle new W sub i's, you get to the point where you have to worry about where the Wi lives. And you can rule out all the cases that we've mentioned so far. So for example, you can assume W1 is not equal to XP. We know W1 is not W0. And we can also now, by what we just said, assume that W1 is not equal to the pre-image of W0. Because if it is, then you can just let F3 be F2 and that will work. Okay, so now that you can assume W1 is not equal to the 3 points you've already considered, you can just proceed as before. Now, to make the image of W1 live inside the right tensor set, you can just wiggle the function using G3 and use the density of D1 to choose a member of this family of functions that will put the image of W1 into the correct tensor set. Okay, so this kind of explains the idea behind this proof. So to finish, what happens is this defines a sequence F sub n of functions. Given F sub n, you can define F sub n plus 1 if you work out the inductive hypotheses correctly, which we do in the paper. And you have to choose these alpha i's small enough so that this sequence is uniformly Cauchy on any compact domain in the complex numbers. Okay, so that by choosing the sequence of alpha i's small enough, that's essentially what that does is it makes it so that you're not wiggling the function too much. Okay, so you're not wiggling the function because you never want to obtain some negative slope. Okay. Yeah. Okay. And of course, you also don't want to mess up your previous values, right? Okay, but the point is that another point here is that as you define the sequence of functions F sub n, you get agreement on the points that you've previously handled, right? So that's another important point. So that when you take the limit of this sequence of functions F sub n, you get a new function F, which has the properties that you desire. Okay, so you can choose these alpha i's so that the sequence of functions is uniformly Cauchy. That means the sequence of functions converges pointwise. So F is defined to be the limit of the pointwise limit. And then because this convergence is uniform, the function you get, the limit function, is actually an analytic function. Okay, this is the reason, okay, we want this function to be analytic, and this is the reason why we really are looking at these functions in the sequence as being functions from C to C, because we need uniform convergence to imply analyticity. If we know that each F sub n is analytic, we want to conclude that the limit function is analytic. And if these F sub n's were just real functions, then you can't make that conclusion. But if the Fn's are complex functions, then you can. Then uniform convergence implies. If you have a sequence of analytic functions that converges uniformly to some other function, and these are all complex functions, then the limit function is analytic. Okay, so that is essentially a proof of theorem 3. Okay, so Right, so given any partition D of the reals, any point P, any countable set W, there exists an entire function F, meaning a function that's analytic on all the complex numbers, such that the function restricted to the reals is real valued. You restrict the function to the reals, you get a bijection. The function passes through the point P, and then you can control the behavior of the function on this countable set W. Okay. All right, so let's go back to theorem 1, which was about the existence of sparse analytic systems. So how do you use CH to build a sparse analytic system? So remember, sparse analytic systems are these systems of analytic functions that are strictly increasing, indexed by points in the plane, right? That have sort of a two-dimensional sparseness requirement. Okay. So a certain set of images has to be countable, and a certain set of pre-images has to be countable. Okay, so you can use CH to enumerate the reals and the plane. And you, like we said before, you use those enumerations to build a sparse analytic system as follows. Okay, so at stage alpha, we get F sub alpha by applying the theorem that we just proved to the alphth point, as well as the countable set, the countable initial segment of the reals, W alpha. Okay, and essentially there's more to check, but one of the important things is you want to check that for any W in the reals, this set of images is countable. That's one of the sparseness requirements for this family to be a sparse analytic system. Okay, this is the set of all images of W under all functions F alpha whose X coordinate, right? The X coordinate of the point that indexes the function is not W. Okay, but that is quite easy to do because A sub W has to equal A sub W C for some C. And then A sub W C is contained in the union of two countable sets. Okay, and yeah, so I guess I didn't say what DXC was, but DXC is a countable dense set, right? So A sub WXC is contained in DXC union this set, the second set here. But this second set is countable because C is some countable ordinal. Okay, yeah. So the DXC is a member of some partition of the reals into countable dense sets. Okay. And then we can come back to the main result to see how that works out. And again, like I gave you some of the details for theorem 3 here. We went through those details. These, what I'm showing you here for theorem 1 and theorem 2 is a little bit sketchy, but you know, these are actually pretty straightforward. And so for theorem 1, if you assume CH, and we want to argue that it's not true that every set has a good predictor anonymous for the analytic members of strictly increasing homeomorphisms of the reals. CH implies that there's a sparse analytic system. That's what we just talked about. And then, like we said before, you can use a sparse analytic system to build an equivalence relation on the reals, such that if you take S to be the set of equivalence classes, that set has no good as predictor for the analytic members of the strictly increasing homeomorphisms of the reals. Okay, and that the equivalence relation you can define easily using the sparse analytic system F. You just say that two reals are related if and only if there exists some member of the sparse analytic system mapping U to V. Okay, but that member has to be indexed by some point P whose X coordinate is not U and whose Y coordinate is not P. Okay, and you can, this is a definition of the equivalence relation, and then you can check that there's no good S predictor for this set of equivalence classes.
Is it clear that that's an equivalence relation, or do you have to close it up to make it an equivalence?
Oh, let's see. I think it's just an equivalence relation. Let's see. Yeah, it should just be an equivalence relation. Do you see a problem with that, or let's see? It should just be an equivalence relation, but yeah, let's see. Maybe make sure I wrote it down correctly. This is part of the work that Sean did. So let's see.
I guess at the moment, I don't even see the.
No, you're right. You're right. You're right. Yeah. In the paper, it says you use this to generate an equivalence relation. Yeah, you're right. Yes. Yeah. You're right. Thank you. Okay. Any other questions about that, or? Okay. Okay, so this is pretty much it. So the open questions that I have here, these are essentially the open questions that were on the diagram from the beginning. So the first question is CH necessary in this result? So does it follow just from ZFC that there are sets that have no good predictors anonymous for the analytic members of strictly increasing homomorphisms? Okay, so is CH necessary? Of course, CH is necessary to get sparse analytic systems, because that was an if and only if theorem. But or on the other hand, if CH is false, maybe every set S does have a good predictor anonymous for analytic functions. Okay, and then the third question: does every set S have a good S predictor anonymous for polynomials? Okay, I think that third one should be a really approachable problem, probably suitable for an undergrad to work on. Okay, so I'll stop there. Any questions? Let me know.
All right, Brent, thanks very, very much. That was really interesting. And it's amazing that there are still like relatively problems to work on that you can work on with an undergrad student, right? We always think of that you need so much sort of background to do research, but this is really cool.
Yeah. In fact, the student that we worked with, Kayla Lee, she's a really good student, but she hadn't had any analysis yet. So like, we spent half the summer giving her sort of a crash course in basic analysis and set theory, and then we did this in the second half of the semester or the summer. These papers of Hardin and Taylor and Bashpai Velleman, the sort of the results preceding these were in the American Mathematical Monthly, so.
Oh, I see.
Yeah, if you're looking for problems for undergrads in set theory, you can search American Mathematical Monthly for the right MSc code, and there's some stuff out there.
All right, anybody have questions for Brent?
So I have a question. I know I think Tornquist and Weiss, and I think subsequently Sylvia Steiler did some work where they look at sort of classical things equivalent to CH and doing a kind of sigma 1-2 version of it. And in every case, they found that was equivalent to the every real is constructible. So I'm just curious if kind of these equivalents of CH, whether that would work as well for them. So
Yeah, that's a good question. I don't know. Let's see. So
Yeah.
who was the third author you mentioned? Tornquist.
So
Weiss, and-
Tornquist and Weiss did some work, and then I know about it because Sylvia Styler did some work on it subsequently. So yeah.
So would there be a conjecture on your part?
I mean, the conjecture is that anytime you find something equivalent to CH, like this Erdish result or these other variants, and if you kind of change it to be sigma 1 definable, this kind of sets you're talking about, then actually that will be equivalent to every real is constructible.
Oh, I see.
So,
That's interesting.
yeah.
I'll have to take a look at those. That work. Yeah.
I can send you the list of names at least if you like. So yeah.
Okay, sure. Yeah, we can do that.
Anyone else?
Let me speculate about something. The definition of predictors used measure zero, but you mentioned that they're actually countable, so they're very measure zero.
Okay.
If you change the concept of predictor, you can have the measure zero version, you can have the countable version, you can have a bare category version, you can have various notions of smallness for the places where the exceptions happen. Is it reasonable to expect that those different concepts are going to end up giving you the same answers to the open questions at the end, or is there no visible connection between them other than the obvious things like countable sets have measure zero?
Yeah, that's a really good question. Another one I don't know the answer to. Yeah, I'm not sure what to say.
Okay.
I mean, as far as I know, that's never been looked at before, so that would be another good direction to go in. Yeah.
Yeah, that's sort of an open question about the open questions. So
Yeah.
super open.
Yeah. I think Sean has thought about a few other problems in this area, so he might have a longer list of open questions, and maybe he's given that some thought, but I'm not sure. Yeah, as far as I know, no one has considered any of that. Yeah.
Okay.
Thank you for, yeah, thanks a lot for the really good questions. I appreciate it.
Anyone else? All right, Brent, thanks again. Really fun.
Thank you. Yeah.
Yep. Thank you. Great chat.
Okay, we're not meeting next week, right? We have a schedule, I think.
Okay.
Yeah, I mean, I think so. I don't remember, but I'm pretty sure we're not meeting next week.
Okay.
All right, so.
All right. Nice weekend, everybody.
Yeah.
Thanks again.
Thanks, Brent. Bye.
You're welcome. Bye.